Hello friends, welcome to my channel Computer Engineering Made Easy and I am Anindita. In this video, I will discuss about the concepts of stack memory using an example in C. If you are looking for a tutorial on stack data structure, you may skip this video and check out the description box below for the link of my tutorial on the stack data structure. In this tutorial, I have discussed an example that exhibits the behavior of the stack memory clearly. Stack memory happens to be one of the various segments of the memory pool in C. I recommend watching my tutorial on memory pool in C, whose link is given in the top right corner of the screen prior to watching this video. If you have already seen it, let's continue. The memory pool in C is divided into predefined sections, and these sections have specific locations with respect to the memory addresses. The stack section, or the stack memory as you know, is used to store the automatic or local variables whose scope is valid within the function where it is declared. It is divided into successive frames where each time a function is called, it allocates itself a fresh stack frame. The stack grows and shrinks in one direction as the frames are created and destroyed. Every time a function is called, a new frame corresponding to it comprising of local variables in the function is created and pushed into the stack. Once the function completes execution, its corresponding frame is popped from the stack. It follows last in first out order. So the frame executed last is popped out from the stack first. The top of the stack is marked by a specific pointer variable called the stack pointer. It is basically a CPU register. Now this is exactly what we will see today using a simple example. In this example, we have considered 4 functions, namely fun1, fun2, fun3 and fun4 apart from the main function. The functions fun1 and fun2 are called from the main function to find the sum and product of first n positive integers respectively. Finally, the main function displays the result. The functions fun1 and fun2 in turn call the functions fun3 and fun4 for finding the sum and product of 2 numbers respectively. Now, let us see what to expect when we execute the program. As we hit the compile or the debug button, the operating system calls the main function. Accordingly, a frame corresponding to the main function is created and pushed into the call stack. The operation push is associated with the call stack, which means putting something into the stack. The operation of taking something out of the stack is called pop. These terms come as a part of the definition of the stack and we cannot change these terms. Since the frame corresponding to the main function is now on the stack, the top of the stack, which is marked by the stack pointer, points to the frame corresponding to main. As the main calls the function fun1, a frame corresponding to fun1 gets created and pushed into the stack. The stack pointer now points to the frame of fun1. As the function fun1 calls the function fun3, a frame corresponding to fun3 is created and pushed into the stack. The stack pointer now points to fun3. Note that as the functions are getting called, the value of the stack pointer is decreasing as it is growing towards the lower address. Now when the fun3 completes execution, its frame is popped from the stack and the stack pointer goes back to pointing fun1's frame. In this case, the stack is in shrinking phase. Hence, the value of the stack pointer increases. On completion of the execution of fun1, the frame of fun1 will get popped from the stack and the stack pointer will now point to main function's frame. The main then calls the function fun2. A frame corresponding to fun2 is thus created and pushed into the stack, with the stack pointer pointing to it. As fun2 calls fun4, again a frame corresponding to fun4 is created and pushed into the stack. The stack pointer now points to the fun4's frame. In this case, the stack is again growing and the value of the stack pointer is decreased. As fun4 completes execution, the control returns back to fun2 and the frame corresponding to fun4 is popped from the stack. Similarly, when fun2 completes execution, the control returns to the main function and fun2's frame is also popped from the stack. Finally, when the main function completes execution, the frame corresponding to the main is also popped from the stack and the stack becomes empty. So, it is now clear that the stack has got only one end through which both push as well as pop occurs. It is also clear that the frame that enters last leaves first. Hence, we say that stack follows the last in first out order or the LIFO order. In the subsequent part of the video, I will show how the values of the variables change during the program execution. I will also show how the state of the call stack changes with each function call along with the value of the stack pointer. Now, in order to see how the state of the variables call stack and stack pointer changes, we need to run the program in debug mode with the breakpoints set against each statement of the program. Here I am using code blocks for running the program. As we start debugging the program, the control first stops at line number 11. At this stage, note that the main function has formed a stack frame and is currently at the top of the call stack. In the watches window, note the state of the frame. In the frame, we have the local variables of the function, that is f, n and w. Currently, all of them are holding garbage value. Another important value to be noted is the ESP register of the CPU. This register is the stack pointer and holds the address of the top of the call stack. Note that the address is currently 0x60FEE. After executing the printf statement, the control is now waiting to execute the line number 12, that is the scanf statement. Since the printf statement has been executed, the string enter n is displayed in the console. Now we enter 5 as the value of n and execute the scanf statement. So the control is now waiting to execute line number 13. Note that the value of n has changed to 5. W and F are still holding garbage as no value has been assigned to them yet. Now on executing the statement W equal to fun1 of n, the function fun1 is called and the value of n, that is 5, is passed as the function argument. Note that the control has jumped to line number 22. In the call stack, the frame corresponding to fun1 has been pushed. Accordingly, the address stored in the stack pointer has also changed to 0x60FEB0 from 0x60FEE0. Now, in the hexadecimal number system, the value of B is less than E. Thus, it is clear that the stack is growing towards the lower memory address from the higher memory address as shown in the memory map figure. Since 5 is passed as a function argument, it is clearly listed in the function frame under the function arguments in the watches window. Also, the local variables of fun1, that is I and S, are holding garbage values. On executing line number 22, the value of S has been initialized to 0 as reflected in the watches window. However, I is still holding the garbage value. On executing line number 23, the value of I is initialized to 0 and it is reflected in the watches window too. Now, the control is waiting in line number 24 to execute the call to function fun3. Note that the values of S and I are both 0 and will be passed as arguments in the function call. Also note the value of the stack pointer because it is about to get changed. As the function call in line number 24 gets executed, the control jumps to line number 30, that is, to function fun3. Accordingly, the frame for function fun3 is created and pushed into the stack. Note the values of the parameters in the frame in the stack. S and I are both 0 just as they were passed and are listed under the function arguments as shown in the watches window. The address of the stack pointer has also been updated, as you can see, to 0x60FE98 from 0x60FEB0. Again, 9 is less than B in the hexadecimal number system, so it is again established that the stack is growing downwards from the higher address to the lower address. The local variable k, however, is now holding the garbage value. On executing line number 31, the control jumps back to line number 24. Note that the frame corresponding to fun3 has been popped from the stack and the stack pointer has been updated accordingly. Since 0 has been returned by the function fun3, value of s is 0 as shown in the watches window. However, since the I++ of the for loop has been executed, the value of I has now become 1. And since 1 is less than equal to 5, the control has entered the loop and is waiting at line number 24. On executing line number 24 once again, the values of s and I are passed as 0 and 1, and the new frame corresponding to fun3 has been pushed to the stack. Note the change in the value of the stack pointer. The value of k is again updated based upon the values of s and I, which are 0 and 1 now, and accordingly k is now 1, which is returned back to fun1 on execution of line number 31. Fun3 has again been popped from the stack, and note the change in the value of the stack pointer. Also note that the value 1 returned from fun3 is now stored in s and I has been incremented to 2. On executing line number 24 once again, fun3 is again pushed into the stack. This time the value of s is 1 and I is 2. Note the change in the value of the stack pointer. On executing line number 30, k is updated to 1 plus 2, which is equal to 3, and on execution of the return statement, 3 is returned back to fun1 where it gets stored in s. Frame of fun3 is also popped from the stack and the stack pointer is updated. I is also incremented to 3. Now the function is called once again and frame of fun3 is pushed into the stack, thereby updating the stack pointer. This time the values of s and I are passed as 3 and 3. On executing k equal to s plus I, k becomes 6 and this information is exhibited in the watches window. On returning back to fun1, frame of fun3 is popped from the stack and the stack pointer is updated accordingly. The value returned by k is 6 and is updated in s. I is also incremented to 4. Now when the function is called again, the value of s and I are passed as 6 and 4 respectively. The frame of fun3 is again pushed with s and I as 6 and 4 respectively, and the stack pointer is also updated. On executing line number 30, k's value gets updated to 10, which is then returned back to fun1. Accordingly, when returned back to fun1, the frame of fun3 is popped from the call stack and the stack pointer is updated. Now the value returned from fun3 is 10. Thus, s is holding 10 and I has been incremented to 5. Now since 5 is still less than equal to 5, the function fun3 will be called again for the last time with s as 10 and I as 5. Accordingly, the frame for fun3 is pushed into the stack and the stack pointer is updated. On executing line number 30, k's value gets updated to 15, which is then returned back to fun1. On returning to fun1, the frame of fun3 gets popped from the stack and the stack pointer is updated. Now s is 15 and I has become 6 due to I++. And since 6 is not less than equal to 5, the control breaks out of the loop and is going to execute the return statement by which it will return back to the main function. On executing the return statement, the frame corresponding to fun1 will be popped from the call stack and the stack pointer will get changed. Note the change in the value of the stack pointer. The value returned from fun1 is 15 and it gets stored in W. This is reflected in the watches window. Currently, we are in the scope of the main function. So, only the frame corresponding to main is present in the call stack. The frame corresponding to fun1 has already been popped from the stack. Note the updated value of the stack pointer too. Next, as f equal to fun2 of n gets executed, 5 is passed as a parameter to fun2 and a frame of fun2 is created and pushed into the stack. The value of the stack pointer has been updated too. Watches is now showing the frame corresponding to fun2. Presently, both f and I are holding garbage values. On executing line number 36, I will still be holding garbage value, but f will be initialized to 1. Now, as the for loop initializes the value of I to 1, it gets reflected in the watches window. On executing line number 38, a frame corresponding to fun4 is created and pushed into the stack. The stack pointer is also updated accordingly. Since the values of f and I are passed as parameters, f gets copied into the local variable n while I gets copied into the local variable m. Since the values of both f and I were 1, Currently, both N as well as M are holding 1 as shown in the watches window. Now, T is a local variable to fun4 and hence it is holding the garbage value at this stage. On executing T equal to N into M, the product of 1 and 1, that is 1, gets stored in T. On executing the return statement, the control jumps back to fun2. Note that the frame corresponding to fun4 has been popped from the stack and the stack pointer has been updated accordingly. Since 1 is returned from fun4, the value 1 is stored in F, and since I is incremented by the for loop, the value of I is now 2. Now the fun4 will be called again, but this time the values of F and I will be passed as 1 and 2 respectively. On calling the function again, frame for fun4 is pushed into the stack and the stack pointer is updated. Now on executing line number 43, the value of T is updated to 2, which is then returned back to fun2. On returning back to fun2, the frame for fun4 is popped from the stack and the stack pointer is updated. The value returned now is 2, which is stored in F, and the value of I has been incremented to 3. So now, when fun4 is being called again, the values of F and I are 2 and 3 respectively. A new frame for the current state of local variables is created and pushed into the stack. The value of the stack pointer is also updated accordingly. On executing T equal to N into M, the value of T is now updated to 6, which is then returned back to fun2. On execution of the return statement, the frame for fun4 is again popped from the stack and the stack pointer is updated. Since the value returned is 6, the current value of F is 6 and I is incremented to 4. Since 4 is less than equal to 5, the function fun4 is called again with the values of F and I as 6 and 4 respectively. The frame for fun4 with N equal to 6 and M equal to 4 is therefore pushed into the stack and the stack pointer is updated. The value of T is then recalculated to be 24 and is returned back to fun2. As 24 is returned back to fun2, the frame for fun4 is popped from the stack and the stack pointer is updated. The value 24 gets stored in F and I gets incremented to 5. Since 5 is still less than equal to 5, the function fun4 is called once again with F as 24 and I as 5. The frame for fun4 is created with N equal to 24 and M equal to 5 and is pushed into the stack while the stack pointer is updated. The value of T is calculated again to 120, which is then returned back to fun2. On returning to fun2, the frame corresponding to fun4 gets popped from the stack and the stack pointer gets updated accordingly. The value returned from fun4 is 120, which is now stored in F. On executing the return statement, the value of F, that is 120, gets returned to the main function and the frame for fun2 gets popped from the stack. The stack pointer is also updated. Now, the variable F, which is local to the main, will store the value returned by fun2, that is 120. On executing the next printf statement, the sum gets displayed as 15. And on executing the second printf statement, the factorial, that is 120, gets displayed. On finally executing the return statement of the main function, the stack will become empty and no frame will exist anymore. So the windows, watches as well as the call stack and the CPU register will automatically get closed. With that, we come to the end of our today's tutorial. Hope you have enjoyed it. Please make sure you subscribe to my channel and share this video with your friends. Thank you. Bye bye.